Hello, I'm Chad Staddon from the Department of Geography and Environmental Management, and I'd like to talk you through this presentation about some of the links between patterns of water insecurity around the world and the global coronavirus crisis. As we've been living through these historic times and adjusting to life under lockdown, the inability to go about our daily affairs with our usual normal patterns of travel, transport, mobility, and interaction, we possibly have not been thinking about what lockdown looks like and what the pandemic looks like in other parts of the world. What is the problem that links water insecurity and the global coronavirus pandemic? Well, simply put, it's this. Public health authorities tell us that one of the most effective ways of combating the virus is to wash our hands frequently for up to a minute at a time using a combination of soap and water. But what if you don't have access to water necessary for practicing hand hygiene? In other words, what if you live in one of those parts of the world where water is insecure, where it's unavailable in necessary supply or quality to perform basic household functions such as hand hygiene? More than 1 billion people around the world live with this problem. And so, as public health authorities have been emphasizing the importance of hand hygiene in combating coronavirus, this poses an obvious challenge. How are those more than 1 billion people around the world who lack water services meant to exercise hand hygiene? And what is the relationship? What are the relationships, plural, between water insecurity and the global pandemic? 3 years ago, I was working with an international group of scholars trying to develop the world's first cross-culturally validated scale for assessing comparative water insecurity. One of the questions that we asked in that study was specifically about how often have you experienced not having enough water to wash your hands? Little did we know in 2016 and 2017 that in 2020, that question, having now been answered in over 29 locations in 24 countries around the world, would turn out to be very important. Let me find the pointer here. Here we go. So this bar chart, which is tipped on its side, tells us the summary results from the hand washing questions as asked in the Wave 1 and Wave 2 surveys up to early 2018, divided by region: Africa, East Asia, Central Asia, etc. Basically, the taller the bar, or the longer the bar, the more prevalent is the experience of not having had water to wash one's hands. Note in particular the deep red and the brownish bars. Deep red indicates respondents who answered that they were often or always unable to wash hands because they lacked sufficient water. The brown bar represents those households who were sometimes unable to wash hands due to lack of water. Note that although there is considerable regional variation, inter-regional variation and intra-regional variation, there is still significant prevalence of inability to wash hands in all of the study locations, bar very few. In other words, we found lots of households around the world who will have an inability to practice appropriate hand hygiene to combat coronavirus. One of those countries is Mexico, represented by one study site in northern Mexico in our water insecurity survey, and you can see the logarithmic representation of the accumulated deaths to date on this chart. And when we drill a little deeper, it's perhaps not that difficult to figure out why the lack of water services is correlated with increased risk of viral transmission and increased likelihood of morbidity or mortality due to coronavirus. because very often our respondents live in places like this. This is a refugee camp near Idlib in Syria, and as you can see, the housing is of relatively poor quality, often with tarpaulin roofs, quite densely packed, and with very little drainage for water when it rains, and they do experience periodic storms in this part of Syria, and no evidence of piped water services. Here's another image, an aerial image showing the density of housing in a similar camp near to that one in Idlib. Note the relatively poorly constructed and densely packed housing. What you can't see from the image is that this is combined with high levels of unemployment and therefore low levels of disposable income, which might otherwise be used to purchase things like bottled or tankered water, as well as other goods for household hygiene. You could argue that informal settlements, refugee camps, are almost perfect grounds for transmitting and propagating viruses like the coronavirus. In another part of the world where my colleagues at the Asian University for Women have been working, we see more than 1 million Rohingya refugees crossing the border from Myanmar, known as Burma formerly, into southern Bangladesh to these red shaded areas, which are depicted here in 2 zones of refugee camps along the Bangladeshi-Burmese border. Another instance where a large population has been packed together in dense, poorly constructed settlements with poor water and sanitation infrastructure. Perfect breeding grounds for coronavirus transmission. But even in more settled, more peaceful developing world contexts, we see water insecurity. Here's a picture from a queue at a water security tap in Eastern Africa. And this is an image in many ways of water insecurity. If you have to queue at a pail with a spigot in it just to wash your hands, that is indicative of household and personal water insecurity. In one of the study areas where my team works in southwestern Uganda, I'll have more to say about that a little bit later, this is another image of what water security looks like. On the right-hand side, you can see a huge queue of people and the ubiquitous 20-liter jerry can queuing for water, which they're going to take from a source like this. A natural environmental source, which is ephemeral. It's not always present. During the dry season, it is absent. It is only during the wet season that it's possible to take water from this location. And even if the water is of reasonable quantity, that is to say, you can fill your jerry can, it is clear that there are going to be quality issues. In another part of Africa, the problem wasn't availability of water itself, it was the safe access to those water supply points. In this case, we encountered a peri-urban informal community on the edge of Kampala about 10 years ago that was accessing water in this kind of a landscape, and the work we did with the community involved rebuilding access to the same water point so that the community could continue to access the same water in quantity and quality, but to do so safely without risk of injury to themselves, their children, or other members of their family. So what else do we know about this problem of water security, which seems to be intrinsically linked to our global efforts to combat coronavirus? I mentioned earlier that I've been part of a study, an international study, developing a comparative multi-indicator scale for assessing levels of water insecurity at the household scale. On this map, you can see all the locations that we surveyed through 2 waves of survey, versions 1 and version 2, wave 1, wave 2, through the beginning of 2018. To make a very long story short, one of the things we learned is that these are the key 12 questions that you need to ask any household in any community that you want to study anywhere on Earth. These are the 12 questions that seem to be most explanatory, most evocative, and to give you the strongest possible indication of relative levels of water insecurity. And one of those questions is about hand washing. So we have this data set that tells us how many of our respondents have had to go without washing hands because of problems with water in the last 30 days. And what we've learned, as you saw from the bar chart earlier on, is that there is a variable but significant prevalence of hand washing related water insecurity in our study groups in 29 sites in 24 countries around the world. But we also learned that even within sites, there's huge variation. So what I've done on this box and whisker plot is shown you a number of different statistics. So let me talk you through them. First, you have the median value for water insecurity, which is represented by the bar that appears somewhere in the middle of the colored rectangle. Then you've got the colored rectangle itself, which represents one standard deviation either side of the mean. And then you've got the whiskers, the lines and crosshatch at the end, which indicate where virtually all of the observations are located. And so what you can see is that even in locations that seem similar according to their measures of central tendency, like Kampala, Uganda, and Gressier, Haiti, with relatively similar averages, the distribution of results is actually quite different. And what this tells us is that even within a location like Gressier, Haiti, there's huge variation in experience of hand washing related water insecurity. We can unpack the data in different ways. You've got 4 composite bar charts here. I invite you to study them at your leisure as much as you wish, and even if you wish, email me afterwards and we can correspond about the meaning of some of these numbers. But what I want to show you is that the data we have on drinking water source for the same 4 sites in this particular case shows us once again variation in terms of drinking water source, non-drinking water source, how households are treating water, and how households are transporting and storing water. All of this data tells us that simply reporting an average level of water insecurity based on our data is probably not enough. There's huge variation in what that actually means in any given study site. Let me tell you a little bit about what my team at UWE Bristol is trying to do about this global problem. I've mentioned before that we have active activities in southwestern Uganda, in the far southwestern location, the far southwestern district of Kisoro, which is about as far southwest in Uganda as you can go before you end up either in the Democratic Republic of Congo to the west or Rwanda to the south. It's a mountainous region in the Virunga volcanic mountain chain group, and it's a region of relatively rapid population growth, a largely subsistence economy, and relatively poorly developed water services. It is also a region that has long experience of viral pathogens, including Ebola, as recently as last summer. It's a monsoonal region, so it experiences significant rainfall in parts of the year, for example, March to May, has a relatively dry summer period, and then later on, towards the end of the year, it gets a little bit rainy again. So there is incident precipitation, significant incident precipitation, but relatively little infrastructure to intercept, store, treat, and distribute that incident precipitation. Which is why the household water security indicator scores for Kisoro, Uganda are relatively high. In this representation, I've broken out the data in yet another way, showing you how the HY score, the composite index I spoke about earlier, correlates with different sources of water as drinking water sources. And here you can see that the households that report themselves as most water insecure are also those households that tend to depend on unprotected dug wells or protected springs or surface waters of various kinds for their drinking water. Perhaps intuitively it makes sense that those who report depending on piped water, a very small population in Kisoro, Uganda, report themselves to be the least water insecure. I've included in this presentation a link to an 11-minute video made by one of my students 2 years ago describing the activities of our team in southwestern Uganda. And I invite you to click on that link at some later point and review the video if you're interested in learning more about how we're managing problems of water insecurity in locations in the global south like Kisoro, Uganda. I'm going to talk you through it very quickly for the purposes of this presentation. Because Kisoro, Uganda and much of East Africa experience monsoonal precipitation, this creates an opportunity. And the opportunity that we've been working hard with colleagues and partner organizations in Uganda to exploit is rainwater harvesting. Here you see a very clear example of what we're trying to do. In this case, we've actually built a roof with corrugated metal sheeting. That's our catchment area. During rains, the water is channeled through these gutters and downspouts into this ferro cement storage tank. This is a particularly large tank. It's capable of storing about 20,000 liters of water. It's more usual to build tanks in the 5 to 6,000 liter size, such as this one here, or this one that Declan is modeling here. So a lot of our work has been about helping to design, build, and manage ferrocement rainwater harvesting systems at household scale and at institutional scale. But collecting enough water together to be useful is only part of the problem. It also has to be clean enough to be safe to use. So another branch of our work involves looking at the chemical and microbiological quality of stored rainwater. And this is the photograph here, which depicts activities taking place inside a field lab we established in 2018 and 2019. So the challenge is to figure out how to build rainwater harvesting systems of sufficient size, how to place them in the correct locations so that the water is where it needs to be, and then how to manage the quality of that water so that the water is not just in sufficient quantity, but of sufficient quality to use. Just thinking about this first roof structure that I talked about a few minutes ago, you can imagine that as rain falls on this roof, in addition to sliding down the surface into the guttering, it may well pick up deposited debris, leaves, grit, bird droppings, all kinds of organic and inorganic matter could get washed into this rainwater harvesting tank. All of these materials potentially are a problem waiting to happen. There are over 200 tanks built by our partner organizations in southwestern Uganda. And I'll come back to the question of water quality in a minute. I just want to spend a few moments talking about the quality of the tanks themselves. One of the things we've learned through the work we've been doing is that you have to pay very careful attention, not just to the design and engineering of the tanks, but to their actual construction. This body of work reported here and in the next slide involves thinking about why a number of the tanks that we were building in recent years were failing and cracking relatively quickly. It turns out there are a number of ways in which these sorts of structures can fail, some of which are listed down the left side of this table. Let me come back to quality though, because once you've got the tank built in the right place, of the right type, built to a high enough standard so that it won't crack, we need to think about the quality of the water that's stored in it. This table reports from our field season in 2018 data on physical characteristics of water, including pH and turbidity, some chemical constituents of the stored rainwater in terms of metals like zinc, iron, and also chemicals that may be constituent in the stored rainwater, including nitrates, nitrites, phosphates, etc. But we're increasingly concerned about these two rows here, total coliform and fecal coliform. These are measures of the amount of coliform bacteria in the stored rainwater. According to the Uganda Treated Potable Water Standard and the World Health Organization standard for drinking water, there should be no total coliform or fecal coliform in water intended for human consumption. You can see that the standard for natural source potable water is a little more relaxed, up to 10 CFUs or colony forming units per 100 milliliters of water. However, in that field season, we sampled 34 tanks and we found a mean average total coliform concentration of about 490 colony forming units per 100 milliliters, 48 times higher than even the more relaxed natural potable water standard. We also measured for fecal coliform, which is a constituent within the broader category of total coliforms, and found significant fecal coliform contamination within the same sampled rainwater. So we know we've got a water quality challenge. So moving forward, our team is thinking about, there we go. Our team is thinking about development of ceramic point-of-use water filters as one way of helping householders cheaply and efficiently quality assure the water stored in their tanks as they move the water from the tanks to the household for personal use. These 4 tasks were actually part of our list of tasks that we were going to undertake during the summer 2020 field season, which unfortunately has had to be postponed due to the coronavirus epidemic. Obviously, we cannot travel, and even if we could travel, many of the countries we work in, including Uganda, are closed to international travelers, so we've had to put this work on hold. The first task that we've been thinking about involves streamlining our chemical and microbiological testing. We also want to continue our survey of the over 200 rainwater harvesting tanks in the district. We want to do some more household-based surveys of water insecurity, the surveys that underlie the bar charts and the box and whisker charts I showed you earlier. And we're keen to field test ceramic point-of-use water filters as a cheap and locally available way of quality assuring water for human consumption. So that's a fairly quick run through the work that my team and I have been doing in East Africa, generally in southwestern Uganda, more specifically over the last couple of years. All of this work is aimed at improving levels of household scale water security. And as we do that, we expect that fewer households within those locations that are receiving these assets and these benefits will need to report to us in the future that they've been unable to wash their hands as a result of not having access to sufficient quantity and quality of water. And the more households who are able to say that, the more those households will also be able to combat viral pandemics like coronavirus. Thank you very much.